Okay, so this is gas stoichiometry, and where we're going to start is you have to recall from your gas unit the molar volume at SATP, which is standard ambient temperature and pressure, that the molar volume is 24.8 liters per mole, and at standard temperature and pressure it's 22.4 liters per mole. Also, the ideal gas law, which is PV equals nRT, P meaning pressure, which always has to be in units of kPa, V meaning volume, which always has to be in units of liters, N meaning number of moles, always has to be in the unit of moles, T, which is temperature, always has to be in the unit of Kelvin, and then R, which is our ideal gas constant, which is 8.314 kPa times L over mole times K. And then also the law of combining volumes, which is when gases react together to form other gases, the volume of the gases show simple whole number ratios to each other, assuming same temperature and pressure. So an example of that is, so if I have hydrogen gas and chlorine gas, that results in hydrogen chloride. And I have 1 liter of hydrogen gas, and I want to find out how many liters of hydrogen chloride I have. I just use the molar ratio to convert the volumes. So it would also be the ratio of volumes. So 1 liter of hydrogen, for every 1 liter, we have 2 liters of HCl. So then that would give us 2 liters of HCl. So those are the main things that you need to remember for this unit, and then I'll do some example problems. So it's really important also, in every stoichiometry question, the first thing that you're going to do is write out a chemical equation. So number 1, if 300 grams of propane burns in a gas barbecue, what volume of oxygen is required at SATP? So first things that we're going to notice is that we have 300 grams, we're looking for the volume, and they also give us SATP, which means that we have a specific set of conditions of temperature and pressure. And so the first thing that we need to do is write out a chemical equation. So propane has the chemical formula C3H8 plus oxygen. And notice that this is a combustion reaction, so it results in carbon dioxide and H2O. And then we need to balance the chemical equation. So we'll start with carbon. We have 3 carbons here, so we need 3 here, sorry. So that gives us 3. We have 8 hydrogens here, so we need 8 here, but we already have 2. So when we put a 4 in front, 4 times 2 equals 8, so now we have 4 hydrogens. And now we have 2 oxygens here, but we need 6 plus 4, which is 10, so we put 5 there, and then you have your balanced chemical equation. Okay, so now we have 300 grams of propane, and we need to find the amount of oxygen in liters. So Also notice here that all of the reactants and products are all gases. Okay, so in this question we need to find the number of moles of propane. So to do that, we start with the amount that we have, which is 300 grams, and then we find the molar mass, which is 44.11 grams for every 1 mole. And then to convert that to, oh yeah, and then we have, sorry. So to find moles of oxygen, convert by using the molar ratio, which is for every 1 mole of propane, we have 5 moles of oxygen. So we're going to have 1 mole propane. So that gives us 34.0 ... moles of oxygen. Okay, so keep all of your significant digits in your calculator. Okay, so here we use the molar mass, and then that converted grams into moles of propane. And here we use the molar ratio, which converted moles of propane into moles of oxygen. Okay, so from here, we need to find the volume of the oxygen. And there's 3 different ways to do this. So I'm just going to erase this. So we know that we have approximately 34 moles of oxygen. So first way to do this way is really you can only use it when you have a specific set of conditions, which we do, which is SATP. So we know, since the molar volume of SATP is 24.8, and we can use it for this question, because we need to find liters of oxygen. And the molar volume for this is 24.8. Liters per mole. So we just go 1 mole down here, and that crosses those out, and then 24.8 liters. And our final answer is 843 liters of oxygen. Okay, so that's the first way of doing it. Second way is using unit analysis. Since we already have the moles of oxygen, that's 1 step closer. And then we just use the ideal gas constant, which is 8.314 kPa times L over moles times Kelvin. Okay, so, and then that goes on, whoops. Sorry. Since we need to put moles on the bottom, because we have moles of oxygen there, and then this is kPa times liters. So then those cross each other out. So now that we need to find liters, so we need to get rid of kPa and Kelvin. So that means that we would put temperature on the top, and our temperature in Kelvin is 298.15 Kelvin, and those would cross each other out, and 100 kPa. And those are good. So then our final answer is 843 liters of oxygen. Third way of doing it is just using the ideal gas law, which is pressure times volume equals number of moles times the ideal gas constant times temperature. So, to manipulate that formula to find the volume, it would be nRT over P. So then, we don't know what volume is, but we know what the number of moles is in oxygen, so we have 34.0 moles. And then our ideal gas constant always stays the same. And then temperature. And our pressure. And we know all of these because at the beginning of the question it gave us the information that we have SATP. So then for that, we just put it into the formula. So V equals number of moles times ideal gas constant times temperature, all divided by pressure. So, and that gives us the answer of 843 liters of oxygen. So that's the first example. Second example is the Haber process is used to produce ammonia for fertilizer by combining nitrogen and hydrogen gas. Okay, so what volume of ammonia at 450 kPa and 80 degrees Celsius can be obtained from the complete reaction of 7.5 kilograms of hydrogen gas. Okay, so the very first thing that we need to do is write out a chemical formula. So we know that we're combining nitrogen and hydrogen. So nitrogen plus hydrogen forms ammonia, which is NH3. And then we need to balance the equation. So we have 2 nitrogens here, so we need 2 here. Put 2 in front, that gives us 6 hydrogens. So in order for this to be 6, 3 there. And you have a complete balanced equation. Okay, so we know that we have 7.5 kilograms of hydrogen gas. Converted to grams is 7,500. And we need to find the number of liters of ammonia. Okay, so in order to do that, I'm going to use a unit analysis to find the number of moles of ammonia. So we start with grams. molar mass to convert. Then we use molar ratio. So for every 3 moles of hydrogen, we have 2 moles of ammonia, which gives us the number of moles of ammonia, which is 2,475 moles approximately of ammonia. Okay, so I'm just going to write down that we have 450 kPa and 80 degrees Celsius for those. And then number of moles. Okay, so now I'm going to use unit analysis to finish the question. Really, you can just all do this in one step, but I didn't have enough room, so. So we take the number of moles of ammonia to convert it to liters. So if we're using the ideal gas constant, that gives us the unit of liters that we need, and it also crosses out our moles of ammonia. And then we know that we have 450 kPa, so we can put that down here. And then we have 80 degrees Celsius, so to convert that to Kelvin, you just add 273.15 K, which is 353.15 K. So we put that here. So then we end up with the number of liters, which, including all sig digs, actually the answer is 16,150.10 liters. All sig digs, which is 2 degrees, 1.6 times 10